We're going to talk about the principle of relativity. The principle of relativity is very simple. It's just this: all motion is relative. That means that there's no absolute stationary, there's no absolute movement. All you can tell is that there's relative movement. And the principle of relativity comes from Newton's laws of motion. It comes from his first law of motion, the law of inertia, and that simply says that stationary objects are really no different to moving objects. Neither of them have a force on them, and they both look really much the same. They're both natural forms of motion. So here we are, out in deep space, in two spacecraft, and let's imagine here's you in one spacecraft, and the spacecraft next to you is a friend of yours. And not only are you in these two spacecraft, but it appears to you that your friend is drifting at quite some speed away from you. Of course, from her frame of reference, it just looks like the opposite. It looks like you're moving away from her. So let's think about how would we answer that question. Who is moving and who's actually stationary? Well, we could try and feel things. We could stand in our spacecraft. Well, of course, there's no gravity anywhere. Our spacecraft is moving at the same speed we are. There's no net force on us because of Newton's first law of motion. So the spacecraft's not going to be pushing on us. We're not going to feel any kind of thrust in our seats as we're moving at a constant velocity. It'll feel exactly the same as if we were stationary. So you think you're stationary because you can't feel any movement. She thinks she's stationary. That's not going to work. Well, let's perform an experiment. Let's imagine that you get a ball and you decide, okay, I'm going to do an experiment here. I'm going to let go of this ball and see what the ball does. Well, the ball, when you let it go, what's going to happen? Well, it's going to stay exactly where you let it go if you were stationary. Of course, if you're moving with a constant velocity, let's imagine that you are actually the person moving in that direction away from her and she's stationary. If you were moving at that constant velocity, of course, the ball would have that initial velocity as well. So when you let it go, it's going to continue to move with you. And so in your frame of reference, it would look like the ball is stationary. You still can't answer the question whether it's you that's moving or whether it's her that's moving. And likewise, if you gave her the ball for her to perform, even though she hasn't got arms, for her to perform that same experiment, she's going to get the same result. You won't be able to tell who's moving. That's the principle of relativity, and there is a problem with the principle of relativity, which is where Einstein comes in. And the problem with the principle of relativity is that there is an experiment that you can perform to determine who is moving. If light is a wave travelling upon the medium, the ether, which permeates all space, which does seem to make a whole lot of sense, if that is the case, then it provides us a way of actually measuring whether we're moving or not. Just like if we're in a boat on an ocean and the ocean is the medium, the ether, through which things travel, we can tell whether we're moving. So let's imagine, let's just get rid of your friend for the moment. Let's imagine we perform an experiment. Here we are with our torch and we've got a beam of light which we're going to shine out in this direction. Let's imagine that we are actually moving backwards in this direction. What speed would we be able to measure that light travelling through our spacecraft? Well, it's simply just a vector sum. We're going to go add those two things tip to tail, and we're going to get a vector sum here, and this is, that's the speed of light minus your velocity. In other words, the speed of light, that light beam out of the torch, would appear to be slowed down if we're moving with a velocity to the left. And of course, if we turn all this around, our experiment around, just to confirm our findings, and turn our torch around, and we're going to move down here for the moment and shine our torch beam, our light beam out this side here. Well, what's going to be the vector sum of it now? It's going to be the addition of those two. And so now we're going to measure the speed of light as being the speed of light plus our velocity. In other words, in one direction, the velocity of the light beam leaving our torch in our spacecraft is going to be slower compared to the other one. And that actually then provides an experiment in which we can violate the principle of relativity. In other words, we can violate the idea that you can't tell whether you're moving or whether the other person is moving. Okay. What Einstein did, and here's his genius, is he said, let's just assume that light doesn't violate the principle of relativity. Let's assume that whatever your velocity is, whether you've got it or not, that when you shine your torch out here, you are always going to measure the speed of the light leaving that torch as a speed c, whether you're moving or not. And in fact, in the opposite direction, if you shine it out that way, it's going to be the speed of light c as well. In other words, let's assume that everyone measures the speed of light in a vacuum as the same. So if that speed of light, that light beam then had travelled and reached your friend over here, even though there's relative movement between you two, she would still measure the beam of light at c. Now that's really weird. There's relative movement between the two of you. You're going to measure this at the speed of light c, how is it that she could possibly measure the same light beam travelling at the same speed when it's coming from a torch which is moving away from her or she's moving away from it? Well, let's just not worry about how that works at the moment. Let's just start with Einstein's assumption that the speed of light is constant for all observers in a vacuum. What that simply means is that relativity is preserved. There is now no experiment that we can perform, whether it's with a ball or whether it's with a torch, to determine whether we're moving or whether we're stationary. In other words, relativity, the concept of relativity existed before Einstein. What he did was he said, let's get rid of this annoying thing, this light experiment that we can perform. And he said, let's just assume, no reason for assuming this at the moment other than it's nice and logical and makes good sense. Let's just assume that everyone's going to measure the speed of light as the same in a vacuum, and the consequence of that, the implications for that is that the principle of relativity is restored, but it has a whole lot of other implications as well, and we're going to be looking at them.